Hey, this is Mrs. Weavy, and I'm back for Unit 9, Video Lesson 6 on the strength of acids and bases. So we can classify acids and bases by how strong or weak they are, and that depends on the degree to which they ionize, dissociate in water. So if we take a look at hydrochloric acid, for example, hydrochloric acid will completely ionize in an aqueous solution. So if we take some hydrochloric acid, as a gas and bubble it into some water, it's going to completely ionize into hydronium and chlorine ions. And that is indicative of strong acids. They completely ionize. On the other hand, weak acids only slightly ionize in aqueous solutions. So ethanoic or acetic acid, chemical formula, when we add it to water, we will get some hydronium and some acetate ions. But look at the direction of the equilibrium. The equilibrium favors the reverse direction, which means that it favors the ethanoic or acetic acid before it actually ionizes in the water. So you actually, at equilibrium, you have a mixture of undissociated ethanoic acid and the dissociated ions, hydronium and the acetate. All right, and here you can see the relative strength of our strong acids, and then we have the bases on the bottom. So here we're starting with the weak acids and increasing to your strongest acids are hydrochloric acid, nitric, and sulfuric. And notice it doesn't matter how many ionizable hydrogens that you have. It all dependent on whether or not they ionize completely in aqueous solutions. And then likewise, we have our weakest of the bases, ammonia, and we work to the strongest of the bases, potassium hydroxide. All right, let's take a look at this table. So it just gives us a different picture of the dissociation of a strong acid and a weak acid. So HA is represents an acid, and it will completely, so a strong acid we see completely dissociates into hydronium and the negative ion. Okay, so HA stands for hydrogen and the anion. And then we see in the dissociation of a weak acid at equilibrium, we have this mixture of the undissociated acid and the hydronium and the anion. But take a look at the concentrations. So we see that the concentration of the actual acid has decreased a little bit, and then the hydronium and the anion had increased a little bit. Okay, but here we see that the concentrations of hydronium and the anion are equal to that of the acid before it had dissociated. Okay, so we can express the strength of the acids and bases by the acid dissociation constant. And if we take a look at ethanoic or acetic acid, it's the same acid, just two different names, ethanoic or acetic. And we have the equilibrium equation. We can express the equilibrium constant as the product of the products, okay, over the product of the reactants. Okay, so that we learned about, in the last unit, how to write an equilibrium expression. So we take our products, multiply them, divide them by our reactants, and multiply those. So how does this actually relate to acid dissociation? Well, we relate that to what is called an acid dissociation constant. And that is the ratio of the concentration of the dissociated form of an acid, that would be your products, to the concentration of the undissociated form of the acid. So the dissociated form is going to include both the hydronium ion, okay, and the anion. So the equilibrium constant multiplied by water, so we're taking the water out of the bottom here, is going to be equal to the acid dissociation constant. So we're just really removing this variable that we have here, the concentration of water. Okay, and so we can then rewrite our acid dissociation constant as the products, which is the hydronium and the acetate, divided by the concentration of the undissociated acid. All right, and that is how we calculate an acid dissociation constant. Okay, but what does that actually mean? All right, now another thing that we can call an acid dissociation constant is an ionization constant, because that's what we're looking at. We're looking at the fraction of an acid that is actually ionized. So weak acids are going to have a very small ionization constant, and then strong acids are going to have a much larger acid dissociation constant. So if we compare these two, nitrous acid, okay, has an ionization constant of 4.4 times 10 to the negative fourth, but ethanoic acid is 1.8 times 10 to the negative fifth. If we look at those exponents there, times 10 to the negative fifth is much smaller than times 10 to the negative fourth. So what that means is that the nitrous acid is going to ionize more, is going to dissociate more than ethanoic acid. So therefore, nitrous acid is stronger acid than ethanoic. Okay. The other thing that we can see too is that the more protons, hydrogen ions that can dissociate, the smaller that acid dissociation constant is going to be. So phosphoric acid, for instance, the formula is H3PO4. So notice that when one hydrogen ion dissociates, the acid dissociation constant is 7.5 times 10 to the minus third. And then when we lose the second one, now we're times 10 to the negative eighth. And then by the time we get to the third one, that's times 10 to the negative 13th. So it's very, very small, meaning that when you get to HPO4 negative 2, that is a very weak acid compared to H3PO4. Okay, so that is the end of video lesson number 6. This is Mrs.